So good morning, everyone. So thank you for the introduction. So today I'll present a little bit about work package number 4, so electron optics and detectors, and I'll focus most of the talk on these event-based detectors and their application for electron microscopy. So I forgot to say that, so I'm a researcher at the CNRS. I'm working at the Solid-State Physics Laboratory in OSE, and also a member of University of Paris-Saclay. All right, so first I'll give a small overview of the work package, and so briefly say who we are and what we're trying to achieve. And then most of the talk will be focused on what are event-based detectors and what they can be used for electron imaging through electron diffraction, and also for a different sort of spectroscopy experiments inside the electron microscope. So I won't describe all the partners. We are quite numbered, but I just put them up on the slide so you can know who are working on this sort of experiments within INPRESS. And so the work package, as I said, it's focused on electron optics and electron detectors. So the first part on electron optics is focused on modifying the phase of an electron beam to phase shape it. So that I won't have time to talk about here today. We're exploring two sorts of technologies with different partners. So either electrostatic phase plates or optical phase changes using a PNM, a sort of a laser-induced phase change on the electron beam. For today, I will only talk about the experiments focused on event-based electron detectors for either diffraction imaging or for electron spectroscopies. All right, so first I'll start with what are event-based detectors and why we are using and what's the current implementation that we are using within INPRESS. So first of all, a quick word on electron microscopy. I don't know what's the background of everybody who's in the audience, but basically on an electron microscope, at least in a STEM, a scanning transmission electron microscope, we have some electron optics and an electron source that allows us to generate an atomic size electron probe that we can scan on a sample. And then we can collect, of course, different signatures. The electron scatters. If we consider elastic scattering, that's what is linked to electron diffraction and some types of electron imaging, we can generate images such as this one I'm showing on the left. So this is an aluminum nitride nanowire with gallium nitride quantum disks. So because of the type of scattering that we select, so this is annular dark field, we can have contrast which is proportional to the atomic number. So we can link and see in the image the gallium nitride quantum disks, which are heavier than the aluminum nitride substrate or nanowire. Because our beam is so small, we can actually image individual columns, and in the limit of very thin sample, so this is a monolayer of HBN, we can see individual boron nitrogen atoms and also individual pigments. And then for what I do, the more interesting part is not the spatial part, but the inelastic scattering that allows us to do a different sort of spectroscopy. Today I will only talk about use, so electron spectroscopy, that in the optical range is linked to optical extinction, and to cathodoluminescence, so light emission from a sample which was excited by the electron beam, which allows us to map the excitation of different decay channels in the material. So I use the same example of the nanowire of containing gallium nitride disks. So we can actually map what's the emission energy of each of the disks by just scanning the electron probe on top of the material. And of course, we have to collect this light. So we use a parabolic mirror. At least for us, we can use any sort of mirror to collect light. A parabolic mirror will help you maximize the collection, your solid angle for light collection. And then we just analyze this light outside the microscope using a photomultiplier or an optical. All right, so what are event-based detectors? So typically, most of us are used to using frame-based detectors. So globally, these are 2D arrays that allows us to measure the amount of electrons that are arriving on your sensor at a given pixel. So you just have a map of number of pixels which are with a given intensity. So this is typically what we do using a CCD, a CMOS, or this new direct electron detectors, such as the MAPS and the hybrid detectors, like the MADI-PICs. The event-based detectors are completely different. The idea is that you have also a 2D array of pixels. Well, it can be a 1D array, but usually it's a 2D array currently. And for each pixel, what happens is that whenever an electron arrives, we time tag it, and then the output is just the pixel which was irradiated and the time when the event took place. So in the first kind of detectors, we have an array, always a 2D array of pixels that can be 0 or non-zero if you have some intensity. In the second case, we just have the list of the number of electrons which are arriving in the detector, when they arrive, and which pixel. So the big limitation for the first kind of detector is that they are limited by the readout time. So globally, you have to read the whole frame at each acquisition. So typically, even for the fastest detectors nowadays, the smallest acquisition time is of the order of a few tenths of microseconds. However, if you use an event-based detector, you're not limited by the readout time because you're not reading the whole frame at each time, but you're limited by the data flow. So basically, the amount of numbers you can get out of your detector. So typically, just to give you an idea, on a given 2D array, you have something of the order of 1 million pixels. Of course, it depends on how you encode how many bits you're going to get out. But if you're trying to encode all the electrons that you're getting in a data flow, even if you use a picoamp, which is not a lot of current for an electron microscope, standard electron microscope, you still have about 1 million electrons per second. So quite quickly, you can accumulate a lot of data. So the reason why we would use this detector is if you want to have temporal resolution and if you want to scan really fast. So the first application is scanning, so just to show you visually what's the difference. So this is an experiment that was performed here in our lab just for demonstration purposes. So we're scanning, on this image I'm showing, we're scanning an electron beam on top of sample, so it's just a metallic structure. For each pixel, we acquire a spectrum, and then the rate at which we can scan is limited by how fast we can acquire each frame on our detector. So this is a CCT used for cathodonescence. And so the fastest we can scan is something of the order of 10 milliseconds per pixel. So that means that the whole frame is going to take maybe tens or hundreds of seconds, at least. If you're using an event-based detector, so in this one, it's our timePix 3, what we see is that we can scan as fast as you want. And because we know it, when the electron scatters on the material and we know where the electron beam is at each time, we can fully reconstruct our data set by just scanning really fast. Each frame takes 10 milliseconds instead of taking hundreds of seconds. So a big benefit of this, and one of the things that we're trying to explore within Impress, is what are the benefits of scanning so fast during data acquisition for beam-sensitive materials. So just to describe the current implementation that we are using of an event-based detector here at LPS, we have a timePix 3 cheetah. So timePix 3 is a class of detectors that were standardized by the CERN, and they are produced commercially by different companies. The one we have was purchased from Amsterdam Scientific Instruments. So just to repeat, the output of the detector is when an electron arrives, we have a resolution of about 1.5 nanoseconds, and in which pixel. As I said, the big limitation for this detector is actually the detection rate. So if you could spread out your dose throughout the detector, you can detect in each chip about 20 picoamps. But in reality, because the dose is never completely spread out, we usually work with currents between a picoamp and at maximum 10 picoamps. So that's a big limitation for this detector. What's important from it is that we have this flow or this list of electron events as a function of time, and we can, at the same time, acquire other temporal information from, for example, the scanning unit, where the beam is at each position, but we can also use it to time tag either some other events like an emission of a photon. That's what we're going to describe in the second part of the seminar, but also the time at which you stimulate your sample. So this kind of detector could be very useful to performing in situ experiments where you can control your stimulus rate. And I'll try to show an example of that on the last slide. So you can trigger any external events. In our cheetah specifically, we have 2 external time-to-digital converters, which makes that quite easy. So we can have at the same time our stream of electron events and 2 external weather events. We use it for the scanning unit and our either photon detection or laser excitation. So why would you use this sort of detector? We have to keep in mind that we cannot detect a lot of current, so that's the biggest limitation, but they're quite useful if you want to scan your beam quite fast on your material, because then you don't have you're not limited by the dead time of the detector. We can have temporal resolution in an electron microscope that does not have a post-electron source, and we can trigger external events, so it's quite useful for in situ experiments where temporal resolution of 1.5 nanoseconds is good enough. So if you want to go faster than that, of course, this technology is not adapted. Right, so just an example of what people within Impress are doing using the timePix 3 for 4D STEM. So this was done in the group of Joverbeck at the EMAT in Antwerpen. So globally, I won't have time to describe 4D STEM and typography in many details, but globally, what we do in this experiment is that we have some material. We can scan the beam on top of the material and then collect diffraction information from it. So at each pixel, you have a diffraction pattern, and then and depending on how you process this data, you can form different sort of images. So you can have the center of mass of your central spot that give you some information. You can generate a virtual dark field, so just reconstruct a dark field from your diffraction data. And you can also do typography. And what's interesting that the group of Yo is doing is that they are developing software coupled to their timepiece 3 to actually do light tachography with fast scanning on your material, with the idea of optimizing tachography for beam sensitive samples. All right, so I should have a video here. Yes. So what's interesting that they managed to do is that they can do live acquisition of the data. So they can get the data stream from the timepiece 3 and in real time do the tachographic reconstruction and have the information this way. So this is not still done for a beam sensitive material. This is for STO, which is very robust, but still it's quite impressive that you can live have the tachographic reconstruction on your screen. Right, so that's it for the STEM. Now I'll move back to electron spectroscopy. That's what I do here in the LPS specifically and within Impress. So just a quick reminder. So I described a little bit about using CL, but just to remind you, the experiment that we're doing is that we scatter a primary electron on our material. It can lose some energy. So if you measure the histogram of these energy losses that's used, this energy can be used to create an excitation in your sample that can diffuse and eventually decay into another particle. In our case, it's close to the visible range photon, so that's cathodoluminescence. And what we want is to understand what's the link between this energy loss and this photon emission, and how the probability of having a photon emission is modified by the actual energy loss that took place. So here in the LPS, we have been studying electron spectroscopy, so using CL specifically in comparison to optical techniques to understand how we can use these electron spectroscopies for nano-optics. So in this example I'm showing the screen, we have a TMD monolayer, a tungsten disulfide monolayer encapsulated in iron boron nitride. And what we wanted to show is that we can, using EOS, which is in orange at the bottom, measure the same excitonic transitions. So if you want, we can discuss afterwards exactly what we are measuring this experiment, but we can see these different excitonic transitions that are also measured using optical absorption. So we have basically the same information that's measured with optical absorption, but with nanometer spatial resolution. And then if you consider cathodoluminescence, so we have this emission from the neutral and the charged extons, which match exactly what we see typically on the same materials using off-resonance luminescence. So what I want to show in the slide, so that's the key message, is that we can do nano-optics using electrons, and we measure, at least for semiconductors, informations which are very similar to what we can measure using purely photon techniques. The big limitation for electron spectroscopy, at least for nano-optics, is that we cannot control the excitation energy. So with a laser beam, it's quite easy to tune the excitation energy. However, for electrons, we cannot control just because of the way electrons interact with matter. So for each electron that scatters in the material, we cannot control which the specific energy loss. And what that leads to is that whenever we have, for example, this stack that I showed before of HBN and TMD, we know that the TMD is emitting light, but we don't know which of the losses, if it's in HBN or in the TMD, that are actually leading to light emission. So what we want to understand is, if we have this loss in the neutral exon of tungsten disulfide, for example, do we see light emission from the neutral exons, or are all this photon emitted streaming from absorptions higher in energy, for example, the HBN substrate? So we have indications that a lot of the light emission events come from excitations in the HBN, but that's what we want to prove hopefully in the near future. So typically in an optical experiment with photons, we can excite a given transition and maybe higher than the band gap of the material. This transition can relax and eventually decay into a photon. The same process is possible with electrons. So an incoming electron that is transmitted to the sample can create an excitation that will eventually decay into a photon. However, because we cannot control the excitation energy, another transition might be excited for a second electron that passes by, and we want to understand if the second transition also leads to light emission, and with which probability compared to the first one. So using photons, we can understand this sort of process by just using a tunable laser source. We can do photoluminescence excitation spectroscopy. We can track what's the emission probability as a function of the excitation energy. And what we are doing currently in the LPS for the last 3 or 4 years is that we are doing a similar technique, but as I said, we cannot control the actual excitation energy per electron. So what we do is we measure them. So for each incoming electron, we measure its energy loss in the EO spectrum. We know its time of arrival because of our event-based detector. And then we can also time tag photon emission event using a standard photon multiplier. And then we can search for coincidences. So this is the actual setup we use. So these experiments were performed in our laboratory about 2 years ago. So it's the same thing I showed you before, but now we have a time resolved electron detectors. We can use resolving time, and also we have a time resolved photon detector. It's a standard photon multiplier with an optical filter to choose which wavelengths we're detecting. So, as I already said, but I want to stress this, we have a stream of electron events with time-tagged energy losses. We have a stream of photons, and then a posteriori, because we have way too much data to process this live, we can do it more or less live currently, but not exactly, because the temporal scale of the events coming out of the time peaks tree are not necessarily ordered. So we can search for coincidences for the events which are ordered. For the ones which are not ordered, we have to post-process the data and search for them. If you want to know why, I can talk to you afterwards, why the events are not necessarily coming out of the detector in order. So we have basically just two lists. Then we search for coincidences, and then from this coincidence, we can build this histogram, which is basically the time delay between the electron and photon with a time resolution. Currently, we can always do experiments at 1.5 nanoseconds. In the past, we had to do some calibration to actually go to 1.5 nanoseconds as a function of energy. So we can search which loss events actually lead to more photon emission events. So the time correlation that you can see is exactly in this point. All right. So within IMPRESS, what are we trying to do? So I'll have to go into the physics of the material to explain why we want to apply this technique to it. So basically, we want to map in space and time, so with nanometer spatial resolution and nanosecond temporal resolution, excitation dynamics in different semiconductors. So I will use an example. So this is the first application that we propose, is to study individual quantum disks of gallium nitride within aluminum nitride nanowires. I can answer you afterwards, Carlos, in a little bit. So in this material, what we know is that typically if you have any semiconductor that is confined, the transition energy of the object of the excitation which is confined can increase because of quantum confinement. In addition to that, in this class of materials, because they're non-centrosymmetric, they have an internal electric field that can shift the transition energies through the Stark effect. So basically, if you have this material, which is quantum confined and with an internal electric field, you have the bands which are bands. And instead of having the transition energy that you expected, for example, close to the band gap of gallium nitride, what you're going to have is a transition which is slightly lower in energy because the electrons are going to localize in the bottom of the well, or the holes are going to localize on the top of the well here. So basically, the transition energy is smaller than the actual band gap of gallium, or the expected quantum confined energy for gallium nitride. So this effect will depend on the width of the well. So the larger the well, the stronger the quantum Stark effect. So if you have a larger well, you can have a significantly redshifted transition line. And what's interesting, that's something which was already known in the literature and something that we're studying in our group for the previous 15 years, is that depending on the excitation rate, you can populate your quantum well with electrons and holes, which are going to create an electric field that screens the first electric field. So you're going to unbend the bands which are bent, and globally you're going to blue shift your transition energy. So that's the first effect. You have a transition which is closer to the expected quantum confined one. And on top of that, I forgot to say, because the electrons and holes are separated in space, their wave functions have small superposition, and the transition rate decreases. So when you screen the internal electric field, you actually increase the transition rate. So you have a blue shift and an increase in the transition rate. So that's what we have been doing within IMPRESS. So this is the work of Jacen Babouha, who was a PhD student in our group. And he was studying slightly thicker wells between 3 and 4 nanometers in thickness. So they have a stronger quantum confined Stark effect. And he was tracking how the emission energy and the emission rate varied as a function of position and the excitation current for this gallium nitride quantum disk. So the idea is to track how the excitation takes place as a function of position. And so this is something we have already demonstrated, that we can track what we expected, the wavelengths. So we do see this blue shift, red shift as a function of excitation current and distance from the well. And the reason why the distance from the well has an impact is because you have charge diffusion and drift in a material that has this internal electric field. The charge dynamics is not the same from one side to the other side of the quantum disk. So that's what we're seeing here. We have fine details that we still don't fully understand. And I've already said these wires were grown by Eva Monroy at the CA Grenoble here in France. And we're collaborating with her to make a model to understand charge drift and diffusion in this material, to understand the fine details of these experiments. So what we actually want to do within IMPRESS, so the next steps, is that in collaboration with Work Package 2, we want to develop or have access to a sample holder that would allow us to perform experiments. I forgot to say that we do these experiments at 100 Kelvin using a liquid nitrogen holder. We plan on doing these experiments at or below 30 Kelvin because, of course, the physics of these materials are going to be much more interesting at this lower temperature. We're going to have access to many other semiconductors that we don't have. We cannot do experiments at 100 Kelvin. And so this is ongoing, and we should have probably a working device in the beginning of next year, hopefully here at the LPS. And the second part that we are planning on working on within Impress is to reach temporal resolutions which are better than a nanosecond. So the first possibility that we're exploring is to use this new generation of time peaks detectors, called time peaks 4, which should at least have a clock time that's faster. So we should approach 200 picosecond temporal resolution, but we have reasons to believe that we might not fully benefit from this increase in the temporal resolution of the time peaks 4. And if you want, we can discuss in the break room why is that, or you can ask me questions yourself in the seminar. And we're also exploring the possibility of using beam blanking to achieve a better temporal resolution within our experiments. And why we're going to go faster and cooler is to first study, as I said already, excitation dynamics. So see how the arrival time of the electron, the charge diffusion eventually leads to a photon emission, and see how this charge diffusion process takes place. And for that, we need a temporal resolution of the order of a few picoseconds to actually see it. And also study charge transfer, energy transfer mechanisms, and also, of course, study faster processes. So with that, I come almost to the end. I just have one slide. Yes, I still have time on other experiments that we are doing, well, in parallel to Impress. It's not exactly inside the proposal, but something that came to us a bit by chance late last year is that we have been doing, it's another research area that we have here in the LPS, is that we do PNM, so photo-induced near-field electron microscopy, and X, electron-image gain spectroscopy. That for these two techniques, what we need is to couple a laser beam into the microscope and make them interact with the electron beam mediated by the sample. So we can actually exchange energy between the electron beam and the laser beam using the near field of our sample as a mediating source. And so in short, in these experiments, we have to shine a laser inside the electron microscope to realize that we can, depending on the conditions we use, so the focus spot that we use, the actual pulse width of the laser beam and its intensity, we can warm up the sample. And then using the time peaks 3, we saw that we can actually track the temperature of a sample with a nanosecond resolution and nanometers spatial resolution. So this is the work that's being done here in the LPS by Fourier and Castiglione. So in short, what he does is that he shines a focused laser beam pulsed. We use 30 nanosecond pulses currently. And we saw that depending on the condition and the wavelengths we use, we can warm up the sample locally. And because we have the time peaks 3 detector, we can know the excitation time or the heating time, T1, because we can time tag our laser. And then we can know when an electron scatters, so we can using the time peaks 3. So we know the time delay between this electron event and the heating event. And because we have many spectroscopy signatures that shift as a function of energy, we can track locally the sample temperature. So here I will only show one example, which are phonon losses in silicon nitride. So basically, we know that if you use a modern electron monochromator microscope, you can see these phonon losses, which for us is a bit high energy, it's 110 millielectron volts. And we know that if you are in a material which is not at zero temperature, you should have also this phonon mode, which is thermally excited. And this is something which is known for decades already, is that if you pass an electron beam close to a sample that has thermally excited excitations, this electron beam can actually gain energy from this excitation. So if you have phonons like the silicon nitride 110 MeV phonons, if they're excited, the electron beam can actually gain. So that's spontaneous energy gain. That's what we see in the electron microscope. We have this peak that appears at the gain side, not in the loss side. And the ratio between the spontaneous losses and the spontaneous gains actually is a quantitative measurement of the local temperature because of the principal balance. I forgot the name of the theorem. Anyway, but it's a quantitative measure of the local temperature, and that's what Florian did. He sent a laser pulse, and then there's a time delay between the laser pulse. So this starts at minus 150 nanoseconds and goes all the way to about 2 microseconds. We see that there's a rise of the spontaneous gain, spontaneous loss peak that shows that actually the sample is warming up. And we have done similar experiments using bulk plasmons in metallic films and excitons in transition metal carbon monolayers, showing that we can track the local temperature using these different spectroscopy signatures with nanometer spatial resolution and nanosecond temporal resolution. So with that, I come to the conclusion. I'll just jump, and I'll thank you for your attention.